Hi, folks. I'm not getting any sound. Is there something wrong?
We're just finishing setting up now.
Okay, thanks.
So I talk into this one.
So this is live mic. I think it was. Would you like to open us up and introduce? Hello, everyone. Thank you so much for joining us online and in person. Welcome to today's Geotalk. Sue's going to introduce our speaker today, but I hope you enjoy it. Sue, you can take it away.
Hi, Susan Webb here for the people online. I'd like to welcome Albin Andreasson.
Yeah.
I'm not quite sure how to say his last name. We've been together for the past couple of days in the field. I'm literally just back from the field, so I'm still in my field clothes, as are some of the students. The neon green doesn't work. We need some lights. So a couple of the new master students also joined us, and if anybody does want to go and visit the ICDP drill site, it'd be really exciting for you guys to come join us. Albin is from Sweden.
Yep.
I keep saying Switzerland, but he assures me he's from Sweden. And he studied at Uppsala, and he actually knows some of the South Africans from the program we have with, for example, Ray and Musa and Glenn and people going back and forth to Uppsala. So I will turn it over to you. He's talking about an undergrad project.
Yeah, sort of, yeah.
And he's just started his MSc and will be working with Freddie Rolisa down at Bloemfontein.
Yeah,
So
correct.
good.
Thank you very much. Yes, my name is Albin, as you said. And yeah, I'm doing my master's thesis on the Bushveld complex, but I've basically just started. So today I will be presenting another thing. It's sort of a climatic period, you could say, and it's been quite a hot debate topic in the last decade or so. I think many people have seen maybe YouTube videos and stuff about it. Anyways, the title of my talk is The Younger Dryas Period, Unraveling Earth's Rapid Climate Shifts. And let's get into it. I'm not sure. Oh, down. No, it doesn't work either. Okay, if I click it. Oh, no, it's still in Zoom like this. I think it's still in Zoom mode. A little hold up. Okay, now it's working. Okay, perfect. So what was the Younger Dryas Period? It was what we call a stadial or a climatic event, which went on for about 1,200 years. So geological timescale, that's not very long. But it's marked by a quite sudden and intense cooling, which interrupted the warming trend which preceded it. And the sort of Earth was in a glacial period, and then the climate started warming, and we see temperatures rising for about 2,000 years. And this period is called the Bølling Høllerud warm period. And then all of a sudden, temperatures drop. And we go back to almost near last glacial maximum levels, which is what Earth was like around 23,000 years ago. And I think this period is very important to study because it helps us understand how and why these climate shifts occur, and also gives insights into Earth's delicate climate mechanisms and how easily they can be interrupted. And I think it's especially relevant today because of, as you know, we humans let out tons of greenhouse gas emissions. So anthropogenic effects which drive modern climate change. Maybe we can, by studying the past, we can also understand how and why climate would change in the future. Another interesting thing about this period is that the end of the period marks the beginning of the Holocene, which is the current time we're living in now. And the Holocene has been a very stable climatic period. And I think that is one of the reasons why we as humans have developed agriculture and then later civilization, because of the climate stability. And but before I go into any detail about the Younger Dryas Period, I think it's really important to put it in a greater context. And this is it's a part of the Quaternary period. And the Quaternary period began around 2.58 million years ago and can be characterized by constant climate oscillations going from glacial to interglacial cycles. And around 90% of the Quaternary period, the Earth was in glacial cycles. And there's a couple of theories on why the Quaternary period started. One of them is the creation of the Panamanian Canal, which happened when South and North America connected, which divided the Pacific Ocean from the Atlantic Ocean. And this intensified the Gulf Stream and also the uplift of the Tibetan Plateau, which also changed sort of silicate weathering in the Himalayas, which changed the ocean so they could take up more carbon dioxide, for example. So there are a couple of factors that science estimate could have caused the Quaternary period. And then also one of the causes is the Milankovitch cycles, which sort of drive the climate oscillations. And as I mentioned, the Gulf Stream, I said the Gulf Stream intensified. And then you may think, okay, how can an intensified Gulf Stream lead to an ice age? That seems kind of far-fetched or paradoxical. But actually, when the Gulf Stream intensified, we get more evaporation and more precipitation over Northern Europe. And then we get more freshwater runoff in the Arctic Ocean, which allowed for these ice sheets to grow. And one of the reasons why we see these constant oscillations going from glacial to interglacial cycles is because of the Milankovitch cycles, which are have three parameters. First, we have the eccentricity, which is Earth's orbit around the sun, going from a more cyclical or a sort of a round orbit to a more elliptical orbit, and has a cycle of around 100,000 years. Then we also have precession, which you can sort of imagine is a spinning object. It wobbles, sort of. And the precession cycles are around 26,000 years. And then we have obliquity, which is the tilt on Earth's axis, ranging from 24.5 to 22.1 degrees. Currently, we're at 23.5 degrees. And you can basically imagine the higher the tilt, the more seasonal variability we will see on Earth. If there was no tilt at all, then we would have no seasons on Earth. The climate would basically be the same all year round. And these cycles together drive climate on Earth. Another interesting period that occurred during the Quaternary is the MPT, which is short for the Middle Pleistocene transition. And here we see these cycles going from 41,000-year cycles to 100,000-year cycles. And this transition occurred from about 1.25 million years ago to around 700,000 years ago. And a couple of reasons for this may have been that we see regolith removal in North America, for example, which sort of enhanced ice sheet stability. Because as the glaciers advanced and retreated, the regolith was removed, and now we have glaciers directly on bedrock, and that is more friction. So instead of sort of advancing fast, the glaciers sort of build up and get thicker and more stable. And then we also have sort of these albedo or positive feedback loops sort of enhancing the cooling over a long period of time as well, which made the Earth more dependent on the low frequency, long duration forcing of the eccentricity cycles. And as you can see, the amplitudes are also higher in the later stage of the Quaternary period, which also meant that we had more differences between the warm and cold periods. And now when we've set some context here and you know a bit about the Quaternary, I sort of want to set the scene here of what the Earth looked like during this time. This image is what the Earth looked like 21,000 years ago. And as you see, we have massive ice sheets covering large parts of North America, Europe, and parts of Asia as well. And in some places, these ice sheets were as thick as 3 kilometers. And sea levels at the time during the last glacial maximum were around 120 meters lower than what they are today, which exposed these vast lands, like the Beringia land bridge, for example, which allowed for humans to migrate into the Americas a couple of thousands of years later. And we have these tundra and steppe landscapes, which stretch across millions and millions of square kilometers. And it was quite a harsh period, very arid and cold. And we have these really cool animals roaming these continents, like mammoths, saber-toothed tigers, giant ground sloths, and more. Maybe you've seen the movie Ice Age. That's a reference, maybe. So now let's define the Younger Dryas period. It began around 12,800 years ago, and it's what we call a stadial. The warm periods in the Quaternary are interstadials, and the cold periods are stadials. So this occurred in the late Pleistocene, and it was first discovered by the sudden reappearance and high abundance of the Dryas octopetala flower, which was found in sediment in Europe. During the warm period which preceded it, the Dryas octopetala flower basically disappeared from sedimentary records, and then all of a sudden it reappears. And this puzzled scientists because this flower thrives in these really cold areas. And then after further research, looking at sort of ice core samples from Greenland, for example, they saw this really big drop in temperature. Some research even suggests that temperatures dropped with as much as 15 degrees Celsius, somewhere between 5 to 15 degrees Celsius in almost a decade. So we have this really, really fast change in temperature. And yeah, as we move out of the Younger Dryas period, this is what marks the Holocene. And as you can see, the last 10,000 years have been really stable. Some key geological evidence for this period is in the pollen from the Dryas octopetala flower, also from ice core samples from Greenland, where we can look at delta 18O concentrations, for example, or carbon dioxide concentrations, and also from sedimentary layers. There's a lot of new research going on actually about terrestrial evidence for these cold periods, which I did my bachelor's thesis on. I looked at the loess soils, which is a fine-grained, wind-blown sediments which accumulates during these cold periods. And combining all of this data, you can get quite a good image of what the climate was like during the time. Now, there are different theories on what caused the onset of this period. The most mainstream and most accepted scientific explanation for the onset of this period is that we had a great freshwater influx from Lake Agassiz, which was a massive meltwater lake in North America. Another sort of quite hot explanation for this that has gotten a lot of attention is that we had an extraterrestrial impact, either a comet or an asteroid, impacting our planet at the onset of this period. And then some new studies also have predicted that it could have been caused by volcanic activity, which together with atmospheric changes could have caused the onset of this period. But before I go through these theories or hypotheses, I want to talk a bit about the AMOC, which is short for the Atlantic Meridional Overturning Circulation, which plays a vital role for understanding the problem. The AMOC brings warm water from lower latitudes to higher latitudes, like the Gulf Stream, for example. And as this warm water goes further north, it evaporates, so it becomes saltier. And then as it gets to these high latitudes, it cools down. And cool and salt water is more dense than warm fresh water. So the water then sinks before turning back south. And the AMOC is not only driven by temperature, but also by salinity. And if we had a great freshwater influx at the onset of the Younger Dryas period, then this most definitely would have affected the AMOC. So a couple of studies on this. As I mentioned before, the period preceding the onset of the Younger Dryas is the Bollerud interstadial warm period. And the Earth was warming for a few thousand years. And of course, during this time, glaciers melt and the sea levels were rising. But not all of this meltwater was immediately dropped or dumped into the oceans. A lot of it was stored on land in form of these massive meltwater lakes. And Lake Agassiz was in any sort of commonly larger than 150,000 square kilometers. Sometimes it was larger and sometimes it was smaller. And researchers have found a pathway along C here, line C, flowing out into the Great Lakes and following the Lawrence River, which dates back, what? Oh, yeah, right. So C here, this pathway along the Great Lakes and the Lawrence River. And this great freshwater influx dates back to the onset of the period. And it's estimated to have been about 9,500 cubic kilometers of freshwater. Then some critics say that a freshwater influx of this magnitude would only cause the AMOC to cool for about 100 years, and then it would sort of go back to normal. And other studies suggest that indeed a freshwater influx like this could have affected the AMOC and as much as causing a cold period for as long as 1,200 years. There's also evidence that suggests that similar periods, like the Younger Dryas, have occurred for many times in the past. So maybe this period isn't special at all. But before I talk more about this, I want to talk about how the Younger Dryas period affected different regions on Earth differently because it by no means affected the Earth equally. The periods or the areas that were most affected were the ones in and around the North Atlantic. In Europe, we see massive expansion of tundra. Carbon dioxide levels during this time were around 180 to 190 parts per million. I think we're currently at 420 parts per million. That's quite a big difference. And so we see these cooling effects on ecosystems and the decline of human populations. Temperatures in January on the British Isles were around 10 to 30 degrees colder than what they are today. But there's still evidence that they were quite warm, but short summers, especially in the Iberian Peninsula and Southern Europe. There were also some great regional impacts in North America. In the northeastern United States, temperatures dropped by as much as 7.5 degrees. And the Laurentide ice sheet, which had been decreasing in size, once again advanced. And the interesting thing about this period is that during the same time, we see massive megafaunal extinctions, which occurred from around, most of them around 13,000 to 10,000 years ago. There's evidence that some of the population started to decline even some thousands of years before the onset of the period, but most of them got extinct in and around the Younger Dryas period. And then I must ask another question here, because as I mentioned, research suggests that similar periods as the Younger Dryas had appeared many times in the past. But during none of these periods in the past do we see an extinction of megafauna even close to the same scale. So if the Younger Dryas period was not unique in terms of climate shifts, then why was it uniquely destructive to megafauna? In Asia and beyond, sediment records from Japan suggest that the onset of the Younger Dryas period occurred as late as 400 years after the onset in Europe. And there were quite minimal impacts in Oceania and Australia. Evidence from Australia even suggests that during the time the climate became slightly warmer and wetter. In South America, there were mixed impacts, but megafaunal extinction still occurred the same, even though they weren't even as close, as strong as in North America, for example. There were also contrasting human impact. In North America, we see the decline of Clovis populations, but there's no evidence for this in North America. And then another question comes up. If climate change was not uniform across the globe, then why did megafauna extinction still occur in multiple regions and in multiple continents? During the time, sea levels changed quite a lot. There were an average increase of around 2 to 4 centimeters per year during the Younger Dryas, which led to a total drop of around 20 to 40 meters. We see abrupt sea level change at the beginning of the period and at the end of the period. At the end of the period, sea levels rose with around 7.5 meters over a period of around 160 years. That would be around 13 times faster than what sea levels are rising with today. And today it's not perceptible to most humans. And even though it was around 13 times faster back then, it probably wouldn't have been perceptible to most humans. But still quite abrupt sea level changes. Now, to go back to the Quaternary period, similar stadial periods, I really want to push this point. Similar stadial cold periods have occurred as many as 20 times in the last 80,000 years, evidence suggests. But the Younger Dryas period is the only one which coincides with a widespread extinction event at this scale. So what happened here? I mean, what caused these megafaunal extinctions if it wasn't special climate-wise? In North America alone, 38 genera of megafauna went extinct. And among these, we have different species of mammoths, saber-toothed tigers, giant ground sloths, the American lion, many really cool animals. Today, most of the cool animals we see are here in Africa. But during the last glacial period, these really big animals roamed Europe and North America as well. And so what caused these extinctions? One new factor that is sort of new for this period that wasn't present during the other periods is that we have humans in the Americas, for example. And there's an argument that humans were the sort of major contributor to the extinction event of these big mammals, because there's evidence for human hunting, and maybe if we have the introduction of a new predatory species into a continent, then sort of these big animals have a hard time adapting. But I don't think there's enough evidence to suggest that humans were the major contributor, because there's only 16 sites in North America where there's evidence for human hunting. And they've only found 5 genres of megafauna, which they are sure humans have hunted. What about the other 33 genres? Did they just, what happened? I mean, if humans really hunted down all of them, then I think we should see a lot more evidence, because during the time, I mean, there were millions of mammoths roaming North America, for example. And, you know, if humans hunted all of them, it seems, I don't know, it seems quite excessive, I think. But, and then there's also evidence that that humans migrated into the Americas a lot earlier than previously suggested. One study looked at a human footprint, which was found in sediments in New Mexico, which dates back to 23,000 years ago. And if there were humans present in the Americas thousands of years before the extinction started occurring, then the argument for the introduction of a new predatory species doesn't really hold the same sort of power, or how to put it. Probably what we see here is that the climate affected these megafaunal populations, and then together with human hunting, these two factors combined could have had, affect the populations so severely, so many became extinct. I don't think I mentioned this. I said, no, I didn't mention this. I should pull up some stats here as well. In South America, 85% of megafaunal species went extinct in and around the Younger Dryas period. And in Europe, around 30 to 50% of species went extinct. And in North America, 70% of megafaunal species went extinct. And the definition of megafauna is a mammal weighing over 45 kilograms. So it's the big ones. So quite high numbers. Now, one of the sort of why researchers have proposed that we might have an extraterrestrial impact at the time is because we see this massive megafaunal extinction. And I want to preface the discussion here by saying that I don't think this is an outlandish hypothesis, but it's also far from a proven fact. The evidence supporting this hypothesis are found in black mat layers in North America, and they are present in around 50 Clovis sites in North America. And these layers contain nanodiamonds, they contain microspherules, and they contain platinum, which are supposed impact markers. But a study from 2014 looked at 49 sediments in Bull Creek in Oklahoma, dating back all the way to around 23,000 years ago. And they did indeed find a similar spike at the onset of the Younger Dryas period. But then they found another spike around 3,000 years ago. And then they found another spike in modern topsoil. So the problem with this hypothesis has been that the evidence hasn't really been easy to reproduce. And these nanodiamonds, they form from high pressure and from high temperatures. And microspherules, there's no real consensus on the sort of importance of their concentrations in these layers, but they can form from wildfires, they can form from volcanisms, they can form from, maybe an obvious explanation for the evidence of these impact markers is that we had actual meteoric or asteroid debris, but Earth is constantly bombarded by space debris, and you don't have to impose an extraterrestrial impact as large as this hypothesis have proposed, because they propose that the impact sort of caused the onset of the Younger Dryas period. It caused these massive wildfires. It caused the extinction of megafauna. I think a strong case could be made if they found a crater, but so far no crater is found. So I think just more research should be done, but it's definitely interesting, and it's good for science. I think that people come up with these hypotheses. Another hypothesis or theory sort of that was published in 2025 from Barken and colleagues looked at tephra from volcanoes. And if we have a very big volcanic eruptions, they can inject a lot of sulfur dioxide into the atmosphere and stratosphere, which form into aerosols, which reflect incoming sunlight, which we know can cause significant cooling on the planet. Even in recent times, we have evidence for this, looking at Mount Tambora in Indonesia or Mount Pinatubo in the Philippines, which actually decreased global temperatures, but they were very temporary. I mean, global temperatures decreased, but it was maybe for 2 or 3 years. So we would need a really big volcano to have a cold period for as long as 1,200 years. But this study suggests that there was one of the largest volcanic eruptions in Central Europe during the whole Quaternary period, and it occurred just preceding the onset of the Younger Dryas period, around 13,000 years or so. And yeah, it could have contributed to Northern Hemisphere cooling, and maybe it's also responsible for some of the impact markers we find in the sediment dating back to this time. So the final verdict here is that most likely the cause of the Younger Dryas period was because of the sort of influx of these great meltwater lakes occurring at the onset of the period, and volcanic eruptions such as this could have definitely contributed to cooling. And I think the Younger Dryas impact hypothesis is very interesting, but more research definitely have to be done before you can say that this is what happened. So in this sort of journey through past climate events, we sort of get an idea of how delicate some of the mechanisms on our planet are and how fast the climate can change. Recent studies suggest that the AMOC has weakened by as much as 15% over the past century. And a publication from Nature last year wrote that a 2-degree global temperature rise could weaken the AMOC by as much as 33%. And this would have severe impacts on climate. In Europe, for example, we would see, because the Gulf Stream would be affected by this, we would see more extreme weather events, more precipitation, and sort of, it's hard to predict, but the climate would definitely change, and maybe it would get even colder. And I mean, I live in Sweden, and I think it's cold already, so even further cooling, that wouldn't be good. So I think it's really important for us humans to mitigate our greenhouse gas emissions. This is crucial to prevent further destabilization and also prepare ourselves for climatic changes, because whether we like it or not, I think that the history shows that the climate on Earth has always been changing. But if we can at least sort of prevent our own emissions, then that's all we can do, and that would be a really good start. Here are some of my references, and that's all I had to say for today. Thank you very much.
Yes. Okay, great.
Yep.
Hi, I'm Rachel. Very good talk. Thank you.
Thank you.
I know you mentioned some of the impacts the Younger Dryas had on a lot of the Northern Hemisphere and Australia. It's been widely debated whether or not it had any impact on Africa at all. I wanted to know if you had any thoughts on that.
No, in Africa, I don't know. I think, but this could have been, I know they found platinum in excess as well. And this was actually in South Africa, heading back to the same time, but they're not sure where it's from.
And no climatic signals that pointed to the same.
I mean, yeah, the northern parts of Africa were affected, but it wasn't that severe. No, Africa was one of the continents that actually survived the best from this period. It wasn't that big of climatic change in Africa. No. Thank you.
Other questions from some of the students? I've got a quick question. What if it was a comet? I mean, a large comet wouldn't leave much evidence.
Yeah, that's true.
Would that be something that could leave the similar signature, or doesn't it not have the
Well, comets are ice.
Yeah.
Yeah, so it wouldn't leave the same signature. I think what the hypothesis here suggested that we have an iron meteorite sort of being air bursting or blowing up in the atmosphere and then sort of spreading out over North America and Europe. But yeah, maybe why we see no crater is, I mean, if it would have hit a 3-kilometer thick ice sheet, then maybe we wouldn't see a crater. But it's hard to say. But a good question. And
the mats, what is that evidence of fires, or what is that?
Wildfires, and also like these organic rich layers form sort of in lacustrine or sort of wet environments as well. They're very carbon rich. But yeah, from wildfires is one of the reasons. Yeah, so there were probably really big wildfires at the time.
Question. Also wanted to ask, what caused the draining of the big lake?
Yeah, sort of. We have like a wall, sort of, you can say. And then when this wall holding in the fresh water bursts, then we get these massive floods.
But why did it burst?
I guess because the water became like it became too filled up. So then it just couldn't. The warming was it get warmer and warmer and warmer, and then suddenly it burst because it's too much pressure. Yeah.
Okay. How do we check online?
I asked to go a bit further back from that. Why did it suddenly get warmer to produce all the meltwater?
Yeah, good
Because
question.
your graph showed a significant warming over a short period of time before the Dryas.
Yeah, good question. I think the graph here is maybe a bit sort of. This was only from Greenland, so temperatures. It was quite regional shift there in Greenland, with temperatures rising, but they were actually rising for around 3,000 years or so. And this was probably caused by the change in Milankovitch cycles. So it was following the normal order of going from glacial to interglacial cycles. So basically what we see is Earth going according to the normal patterns that we see during the Quaternary, where we see Earth going from a glacial to an interglacial. So this was probably nothing really that abrupt.
Okay, any more questions online? How do I get to it?
I got a question.
Sorry. Yeah, you can read it if you want.
How robust is the evidence for humans in the Americas predating the Younger Dryas? It's been pushed back by a few thousand years, and there's a lot of recent studies on this. I mean, the one I showed that's 23,000 years ago is, I don't know if any other have been found that dates back to as late as 23,000 years ago, but there are several others that at least push it back to around 17,000 years ago. So I think a couple of thousands of years before the onset of the period, the Americas were quite populated actually, and you know, as more studies come out, they sort of support the same idea here. So we'll have to see.
Okay, Sherry's got a question.
Yeah, concerning the lack of an impact, an actual impact for that impact hypothesis. Well, that's what you would expect, because most impacts would be in the oceans, as opposed to the continents. But there is also something that I read about maybe 2 or 3 years ago, that there was, with the retreating ice sheets in northern Greenland, there's a possible impact structure that has been revealed, right? But I don't know what age that would be.
I know what you're talking about. Yeah. It's below the Hiawatha Glacier in Greenland. And it was actually thought to date back to this period. But the recent study suggests that it's 58 million years old.
Oh, okay.
Yeah. So,
I guess one last question for me would be, why do you think there was so many more animals went extinct in North America as opposed to elsewhere?
Yeah, I think both, because we have the sort of introduction of humans into the continents. I mean, we had humans in Europe as well, and it wasn't as extensive. But it's probably because humans and also Neanderthals have been in Europe for tens of thousands of years before. So maybe the animals had more time to sort of acclimatize to the living together with humans. But in America, it was quite sudden. So I think probably both the climate and the human hunting had sort of, I don't know how to put it, but more of a quick effect, and the animals couldn't really adapt quick enough. But then also because North America is close to the North Atlantic, so it was one of the regions that was most affected by the climatic changes. Yeah.
Going once? Oh, sorry.
Okay, let's see. I gotta scroll up. I'm trying to remember the fate of the cold water corals of Ireland correctly. There was a warming period some 6,500 years ago, which led to more ice coming down into the northern Atlantic, which cooled the waters too much for the cold water corals for 1,000 years, and led to cold conditions in northern Europe. So yes, Sweden will get colder.
Thanks,
Yeah.
Alan.
Shit. Yeah,
You
exactly.
need to come back to
Yeah, I need
South
to come back
Africa.
here, exactly.
Okay, super. Well, I think with that, we'll thank Albin and also wish him the best with his MSc studies. He's traveling down to the Free State on Monday,
On
I
Monday,
think.
yeah.
So we wish him luck with that.
Thank you.
And yeah, enjoy.
Thank you very much. Thank
you're
you. Thank you
welcome.
all.
Good. I don't know if Robin has any announcements for the upcoming next talk.
Yes, so next week on Thursday, no, but next week we have hosting Professor Richard Golvarb, who's going to be talking in association with SASIG on the origin of gold, the reality, and the fiction. So please join us for that. I'll be sending out that information shortly.
Here we go.